Okay, so now we have all the preliminaries that we wanted, so we can now start with the deep learning itself. So the first thing that we want to discuss is the classical fully connected feed-forward neural network. So if I just say NN from now, if I write NN, you do know that's neural network, so I do not need to all the time say the neural network brackets NN, that's fine. And now, if you have a neural network, you can think, as I told you, it could be in general any sort of combination of the neurons, right? So you're going to have lots of neurons getting connected to each other, and by connection, they're going to get weighted and summed up, right? And there are a bunch of different forms of arranging them together. The most famous ones are, first of all, the classical fully connected feed-forward neural networks. These are the guys, the classic ones that you always think about when you first time think about a neural network. There are a bunch of neurons getting connected fully to anything next, fully to anything next, and so on. And the information always passes forward, right? So there is no case that you go forward and at some point you want to just recurse the information at another layer, right? So this is what we call it feed-forward neural network. The fully connected version of it, some people call it multi-layer perceptron. So it was not very accurate naming, but since everything looks like a perceptron except the activation to be like you put all, you think all of those neurons are perceptrons, right? If you think like that, then this is essentially multi-layering lots of perceptrons to each other. This is why people call it MLP. Typically, this misnomer is somehow conventional instead of using the long-term, fully connected feed-forward neural networks, right? So this is the first classes. The first class of neural networks. The other class is the convolutional neural networks, which are again feed-forward neural networks. Like you again pass the information forward, but they are not fully connected anymore. So they are partially connected through an operation which we call it convolution, and you're going to see it. This is eventually a very good operation when you think about a spatial, like you have image and you want to spatially scan that image, right? Convolution going to do much better than fully connected. It's going to grasp more information or more efficiently the information. You're going to see that. And then last thing, which is going to be an introduction to the sequence model, are the recurrent neural network, which have this opportunity that you go forward in the neural network and you compute something, but you take that computation and feed it back to your neural network because, for example, you want to carry some sort of memory, right? And we're going to see that as well, okay? But today what we're going to do, we want to just stick to this, multi-layer perceptrons. Some people call them the vanilla neural networks because they are the most basic way of thinking about the neural networks. And we want to understand how we can, or how the information gets processed through these architectures, like computationally. And then the second thing is that if we want to just use gradient descent to train them, how we can exactly compute the gradient. Now, one thing at the very beginning of this chapter, which is going to carry pretty much for the rest of the course, is that whenever we get into a new sort of topic, new sort of neural networks, we're going to discuss these two things. How we can do inference. It means that I put the information at the input, like I give the data to my neural network, and it's going to do lots of calculations, computations, till the output, right? It's going to infer from my data something, right? The label. This is one thing that we need to understand, very detailed. And the other thing is that how we can do training or backpropagation, because we need to compute gradient with respect to all parameters of this network, right? And I do know that PyTorch does the gradient, but PyTorch uses backpropagation, and we are here to learn backpropagation. So it's going to be a bit boring, but you really need to know it, right? So please be patient with backpropagation. I'm not going to get rid of it, okay? So now, first thing that we want to understand is that how we can just pass information, the inference bar. And let's start with this MLP case and see how this happens. This is going to be very helpful if we just build this mathematical form that to represent all the process in this network. So this was the classical layered network, and then when everybody's connected to each other, then this is fully connected, the MLP, right? So here, as you see, x1 is connected to everybody here, x2 connected to everybody, and so on. Then the output of these guys are again connected to everybody here, and so on, till the very last one, okay? So every neuron in any layer is connected to everybody in the next layer, right? Now, one question. This x1 that is connected to f1, how do I transfer x1 and process it here? What do I do to x1? I'm going to multiply it by a weight, right? So it means that every single edge that you see here is carrying one independent weight, right? Now, also, if you want to think general, every single of these neurons has one bias, right? So every single of them has its own bias, right? Now, if you have so many layers, and in every single of them you have so many neurons, then you're going to have so many parameters, right? Everybody's cool, right? You see that. Now, right now, what I think that we are processing everything layer by layer. This means that the first layer, or the input layer, goes to the first layer. It's going to get computed, a bunch of values going to get out of the neurons, and then you're going to go to the next layer and so on, right? Later, we're going to see something that we call a skip connection, right? So we can actually connect the input directly to the third layer as well. We can do it as well, right? And we're going to do it later. But right now, you don't think about that. We are just processing layer by layer. Yes, you had the question. Yeah, it's connected. Sorry, it's just a diagram. Just like around that. Yeah, you're right. I mean, xn should be also here. Yeah, but xn is connected to everybody. Like I meant, with this one, I mean like everybody's connected. So sorry for that. Yeah. Okay, so everybody's clear? Okay, now, yeah. So this is what we call it, the fully connected, the MLP. And the MLP, of course, has the input layer. The input layer carries only data, right? So everybody's here. There's no neuron here. We talked about this before. These are the hidden layers. Let's say we have L different hidden layers. And then we have one output layer, which is the layer L plus 1. Okay? This is one MLP. Now, one question. What is the depth of this guy? L plus 1. When do I call it deep? L is more than or equal by 2. L is more than or equal by 2, or L plus 1 is more than 3, and more than 2, equal by 3 or more, right? So if I have at least 2 hidden layers, then it's deep. If I have only one hidden layer, then it's shallow, right? Okay, cool. Now, L is the number of hidden layers. The depth is L plus 1. It's deep when L is more than 1 or at least 2. And then next thing is what we call it the width of every layer. Yeah? So if I am in layer 1, the width of this layer is going to be the number of neurons that I have here, right? So you think about the neural network as a kind of two-dimensional setting, and this is the width, right, in this direction, right? So this is like the number of neurons in the first one, number of neurons in the second one, and so on. One thing that I'm doing here, I'm showing the activation function for every neuron inside every layer to be the same. Typically, this is the case. Actually, in most implementation, we consider any hidden layer to have same activation. We might change the activation of the output layer, right? But like in the very precise design, you typically choose the activation of every layer to be the same. You might change it for the next layer, right? So that's just the convention. As I said, in practice, all of these F1 to FL are the same thing. It might be that FL plus 1 is different, but you're going to see it once we do a couple of examples. Okay? So width is clear, right? Now, there is nothing called width of the network, but I have seen in some papers people just simply say width of the network, and they usually mean the largest width within all the layers, right? So they think like the network is just, two-dimensional thing. and the largest width is the one which is specifying the whole width of the layer, the network, okay? So it's not a kind of universal definition, but you can use it if you want, okay? Now, what I'm going to show from now on, I'm going to show this notation, W, and pay attention, this W is calligraphic, right? W1, W2 till WL, right? So this is the width of every layer, right? Everybody's cool? No worries. The notation gonna get like absorbed in one simple formulation. Hopefully today, not today, early Friday, okay? And then you're gonna get rid of all the details. You know? Do not panic. Now, okay, so this is a neural network. In machine learning terminology, this is a model, so it's gonna have a bunch of hyperparameters and it's gonna have a bunch of learnable parameters. What are the hyperparameters? Depth was a hyperparameter, right? What else? Width is hyperparameter. Activation choices is hyperparameter. Anything of that form is hyperparameter. So how many layers I have, what is the width of every layer? These are the things that we call it hyperparameter. Again, if you want to just implement, you need to choose, right? I'm going to have one MLP with 5 layers. Layer 1 has 100. Layer 2 has 200. Layer 3 has 100 neurons, right? You're going to choose that, right? You first choose it. Once you fix it, then you can count the number of learnable parameters, right? Everybody's clear? Now, what is the number of learnable parameters? For example, in the first hidden layers, I have W1 neurons, right? Every neuron is connected to every input, right? Every neuron is connected to every input, right? So the first neuron has exactly as much as input I have weights plus 1 bias, right? The second neuron in the first layer has as much as inputs that I have plus 1 bias, right? Now, if I want to just think about the first layer, I have W1 neuron. Every single of them has n weights. N is the number of inputs I have, right? And 1 bias, right? Every single of them. Same thing for the second layer, right? I have W2 different neurons in the second layer. You just look at this guy, this second layer. Say, for example, this is second layer, right? And in this second layer, every neuron is connected to everybody before, right? What is the number of weights for the first guy here? W1 plus 1, because it has a bias and W1 different weights. These weights are different. Everybody has its own weights, right? So you can simply say that every single neuron in every single layer is going to have the size of the previous layer, weights, plus 1, right? And then you can write down the number of weights that you have, right? So this is the first layer, n, number of inputs, 1 is the bias counter, and then times W1, right? Again, WL is the previous guy, the previous layer, plus 1, the guy which is taking care of the bias, times the width of the layer, next layer, right? And you can just simply write it down in this form. This is going to be the number of model parameters that you have. This is what people usually say, this is the model size, right? The model size is 10 to the power 9. It means that you have 10 to the power 9 different weights and biases there, right? And you can simply count it down if you know the hyperparameters, right? Everybody's clear? Questions? Okay, no question. Now, if you got that, now let's start with inference, like the forward propagation. This is what we call it, forward propagation of information, or simply forward pass. This means that you start putting your x's at the input, right? x1 to xn as the input at the input of this neural network. These guys are going to get multiplied with the weights, getting added to a bias, pass through an activation, give the first output for the first neuron, right? Same thing happens for the second neuron and so on to the last neuron. Now you have a bunch of outputs at the first layer. They are going to again repeat the same procedure in the next layer and so on till the output, right? And all of these numbers that you are calculating are gradually ending up giving you the output that you want, right? If you choose the weights properly, right? So the whole learning procedure in this process is done by computation. This is what we call it, why we call it computational learning, right? Now, what I want to do, I want to start from the input and write the output explicitly in terms of the input. Okay? Now, it's going to be a bit messy because there are lots of summation and things like this going on. But at the end, I can end it up with a very simple matrix form, which helps us a lot in the future. Okay? I do know some of you see it immediately, like you see at one layer and you say, okay, it's a matrix multiplied with the input vector. That's it, right? But as I said before, I take it like for a student with minimum background, okay? So we're going to do it once together. Sorry if it's a bit boring for some of you. Just please be patient for the others, okay? So now, this is the idea of forward pass. So we have the input. This is going to process over the network, and it's going to give you the output. And the thing that I want to do, I want to just write down how does the output look like in terms of the input. And for doing that, I need to just define a bit of notation, so making everything uniform. So first of all, this is the architecture. And everybody here in every neuron is going to have a bias in general, right? Now, one thing that I'm going to do, I'm going to think about these biases, as I told you before, as weights again, right? So what I'm going to say, look at this guy here. This guy has bias B1, right? So it means that every single body here is going to get multiplied with its own weights, right? And then they are going to add up here. And you add everything up with bias B1, right? Now, I could say that bias B1 is multiplied with the input 1, right? So just to show you once this, making sure that everybody's seeing that. So whatever your first output is, say output of this guy, I'm talking about output of this guy. You see it on the board, this neuron? So when I'm talking about this guy has lots of weights here, right? These weights are getting multiplied with the corresponding inputs, right? So say I have n different inputs, so it's going to be summation of those weights. Right now I'm showing it by Wn. I'm going to change this notation in the slides later, but right now just for simplicity. And every Wn is getting multiplied with the corresponding xn, right? Correct? So x1, x2 till xn, they are getting multiplied with their weights. N adds up from 1 to n, right? And then at the end of the day, you add up the bias, right? Correct? Now, what I can say that maybe this bias is W0, weight W0, and the corresponding input, x0, is 1, right? Correct? And then I can remove this guy completely, and I can say n from 0 to 1, right? To n, sorry. Everybody's cool? Yeah? So I can think of this bias to be, instead of one single weight there, I can simply think of it as an input 1 given to this layer, and then multiply with its corresponding bias, which is the weight, right? Everybody's cool, right? Okay. So I can do it for every single layer. For example, when I go from this layer to this one, then everybody here has its own bias, right? And instead of considering those biases, I can just put 1 there, and then I connect that one to every neuron. Then I think no bias, right? So you can always think about the bias as a weight, so you really don't need to be too much obsessed with the bias, right? So anything that you do without bias is going to immediately extend to the case with bias, right? So this is the first thing that I want to do. Now, the next thing that I'm going to do, I'm going to just give them index. So the input layer, I'm going to call it layer 0. Then we have layer 1, which is the first hidden layer, and so on till layer L. And for the output, I'm going to say layer L plus 1, okay? So these are the index of the layers. That's quite obvious and simple. And then now I have the layers index. Now the next thing that I want to do, I want to just denote the width of every layer. So for the hidden layer, we talked about this. So we said the width of one layer is the number of neurons that I have there, right? And then you're always going to have the number of nodes, not neurons. The number of nodes that you have in every single layer is going to be width plus 1. And that one is the dummy one that I'm adding to take care of bias, right? Everybody's cool? So this guy is index 0, then 1, 2, 3 till WL, right? In every layer. Okay? So for the input layer, I'm going to have n different inputs, right? And then again, one dummy one, which is going to take care of bias, right? So from now on, I'm going to say, when I write down W0, this W0 is essentially n, the number of inputs that you have. Everybody's clear? So width of the input layer is simply the number of inputs that you have. I do know x's are not neuron here, but you can think of them as nodes, which are always putting their value at the outputs, right? Everybody's clear? Questions? Okay, now, and WL plus 1, of course, is going to be the number of outputs, like the last layer, which is the output layer, and this is the output layer, right? Okay, and of course, I mean, we mentioned that we have always, in any layer, we have this dummy 1, which is going to take care of the bias, right? Cool, okay. Now, next thing, I want to index everybody in the layer. That is quite simple. I'm going to give index 0. So if I write j equal by 0 for one particular layer, I simply mean I am talking about this dummy 1, which is taking care of bias. Then this is going to be j1, j2, till j width of the layer, right? Everybody's cool? Yeah? Okay. So this is going to be the case for the index of every node inside the layer. And now, when you move from one layer to another, you have lots of connections, right? Pretty much anyone in the previous layer is getting connected to anyone in the next layer, right? Now, every single edge which is connecting you is essentially carrying one weight with it, right? This is the weight that is going to get multiplied with the previous guy, and then is going to get added to everybody else coming to the next node, right? I am going to show it with this form, WL of j to I. The notation is a bit confusing, I know, but once I compact it in the matrix form, you're going to get rid of I and j, and then you don't need to care about that anymore, okay? Just write now, because this is going to be consistent with what we do later, okay? So what I'm going to do, I'm going to write down the weight of the layer L. You see L here? This is weight that is connecting layer L to the previous layer. Node J is the destination, the node in the layer L, and I is the node coming from the previous layer, right? For instance, here I have W1, Ji, right? So when it's 1, it means that I'm talking about the first layer, right? Now, this first layer is connected to the input layer, right? Now, this W1 is one of the weights connecting the inputs to the first hidden layer, right? And now, if you want to know which way that guy is, J is the index of the neuron inside the first hidden layer, and I is the index of the input, right? Everybody's cool? Now, whatever is at the output here is going to get multiplied with this weight, and there are a bunch of other edges coming to this node, right? All of them do the same process, and they add up, get activated, go out, right? So you must think about the neural network in this form, right? This is only computation, nothing else. I mean, most people who talk about neuroscience, they think our brain works the same. So it's only computations happening in our brain. Neurons are really just doing a bunch of computation, pass it to the next neuron, and so on, when we start to think and decide and so on, right? Okay, so everybody's here having a value multiplied with the weight, going here, adding up, activated, out, right? So this is for the case when I have the input layer. I could have one layer in between, right? So I could be in layer L, particular layer L, right? So anything coming in this layer is coming from the previous layer, layer L minus 1, right? When I say WL, I'm talking about this layer. J is the index of the neuron here, and I is telling me which neuron from the previous layer I'm looking into, right? Everybody's cool? Questions? Yes? Yes, then the story is going to get changed. So it's not going to, I mean, right now I'm not going to do that for you, so I'm going to just consider this MLP, and then I make everything compact in the matrix form. Then you're going to see that instead of showing all of those ways, you just need one matrix of ways multiplied to the output of the previous layer activated. That's going to be the whole thing. And once we have done this, then you can start building those architectures. So they're going to be one other matrix connecting one other layer or input to another layer in between. Yeah? But that's going to just complicate the notation right now. So we think about it later. In chapter 5, we have one chapter on that. Okay? Questions? No question? Okay. So now, considering this one, now the first thing, if I set this I equal by 0, can you tell me what I'm talking about? The bias, great, right? When I set I equal by 0, look at this guy. When I is 0, this means that I am going up to index 0 in the previous layer, right? And we talked about it. Any guy in the previous layer with index 0 is essentially the bias, right? So this means that if you have such a thing, weight of layer L index j and 0 coming from 0 before, that is essentially the bias of that neuron, right? Everybody's clear? Okay, now what if I put j equal to 0? Can I do that? Think about that. Is weight of layer L node 0? Can I do it? No, because node 0 is essentially the dummy node, right? It's not getting any input, right? Right? So you don't have that thing. You don't have WL0I, right? You don't have this guy. So nothing is coming into the dummy node. That's obvious, because that is the bias node, right? But that guy could go out, right? So this guy does not exist. And then this is going to give you a clue about the range of those indices, how they change. But as I told you, don't worry about that. We're going to get rid of all of these indices so very soon. Questions? No question? Great. So if you got no question, the last thing that we need to specify is the kind of output that you could have in every single node inside this neural network. The first kind of thing that we could have is an input, right? When you have an input node inside your neural network, that node is always going to put its value at the output, right? It's essentially doing no computation, right? Is the input coming in, right? It's like you touch something, right? When you touch something, this is the input coming from the surface to your body, right? The neuron is getting those inputs, right? Now, the next kind of thing is this dummy one, which is always putting 1. So it's roughly the same thing as this guy, but its value is always 1, right? And then the key kind of node that we have, which is doing all the process for us, is the artificial neuron, right? Which is getting anything from the previous layer, right? So anything coming from the previous layer is going to get multiplied with the corresponding weights, right? They add up, and then they are getting activated, right? Everybody's clear? So this is the key type of nodes that we have. This is the key type of thing that is doing the process of learning for us. It's just concluding something out of the input. Okay? Great. So now that you have this, what I'm going to do, I'm going to always refer to the output of every single node in this architecture as YL. So L is the number of layer. J is the index, right? So I'm going to say that this is the output of the node J in layer L, right? Everybody's clear? Everybody's cool? Now, if this is the case, now one question. What if I set L equal by 0? What is Yj 0? Y index 0 in brackets J. What is that guy? What is layer 0? Input layer. What is Yj then? is input j, right? So input j, this is going to, so if I say, oh, this one, if I say y0j, then essentially I mean the corresponding input. If I say YL, any layer, and I put index 0, I essentially mean the bias guy, right? 1, right? Everybody's cool? Happy with the notation? I'm not sure if you're happy, but comfortable. Say a better word, right? You're comfortable with the notation? Yeah, we're going to get very soon. We're going to get rid of it very soon. So now, the output of the particular layer, so any layer, other layer than these two kind of input layers, I'm going to write it down YLJ, and this YLJ is essentially the activated version of something, right? This is the kind of soft information you compute before you do the activation, right? So when you are thinking about one neuron, everything comes in, get multiplied with the weights and add up, and then they get activated, right? Before getting activated, that is the kind of soft information you have. And I'm going to show it from now on most of the time by Z. This is the typical notation. And if I want to write down ZLJ, can you help me writing it down? What is going to be? Exactly. So you're going to have, say, let's think like this. We're talking about node J in layer L, right? So WLJ going to remain here. Then from node I in the previous layer, I'm going to get the output of that node, right? So this is the output of the previous layer at node I, right? And then you're going to get multiplied with its own corresponding weight, right? And then I'm going to sum it up. What is the index that I should sum over? I, exactly. So I'm going to add I1 to L minus 1, right? Anybody else in the previous layer, right? And then we usually have a bias as well, right? We talked about this. So the bias would show up. So this is the bias, right? So this is the bias in the layer L for node J. I put index 0, right? This is the bias. It's getting multiplied by 1, right? So I can, instead of 1, write it down YL minus 1, 0, right? So this is what we said. So if we have index 0, in the brackets, if we have 0, then it's always 1, right? And then instead of doing this, I can simply write it down as one summation, right? So I do not need to distinguish between bias and other weights, right? So moral of the story, everybody from the previous layer is getting multiplied with this corresponding weight, and then they add up, right? This is the soft information. You have the soft information is a number, right? Maybe 1,000, maybe minus 10, maybe 0.0001, and then you activate it. You pass it through the activation function. Yes?
The thin layer is the bias defined for L plus 1.
Sorry, I didn't get the question.
The third layer we have
Here?
Yeah. No, up.
Up here?
No, like since j equal to 0 is the constant node.
J equal to 0 is the constant node, right?
Yeah, so L is defined for
Every layer, right? 0 to L plus. No, it should be L. Sorry, you're right. It's a typo. Sorry. This plus 1 should not be there. Thanks. It's a good point. So slide 18. Okay. So this guy, your friend is right. This L should not, I mean, you don't connect the output layer to anything else, so you don't really need the bias there, right? So, but like you can drop this plus 1 here. Questions? No question? Everybody's cool? Okay. So this is the process. Now let's see how does the forward pass look like. So you're going to have these inputs in the previous layer, right? So, sorry, you're going to have these outputs in the previous layer. This is the output of the previous layer. I can just collect them in one particular vector. So we're going to do it now. And then once I have this, I'm going to connect everybody to the next layer. I'm going to do the calculation of the soft information, and once I have the soft information, I am going to activate it. Okay? Now, in order to shorten the notation, I start with the first simplification. I'm going to show this vector YL minus 1. You see it? You see the vector? And the vector is written in bold, right? That vector is containing everybody here, including that dummy 1, right? What is the size of this vector? Exactly, WL minus 1 plus 1. So WL minus 1 are the nodes plus 1 the dummy guy, right? You have this vector. Now, for everybody here, I'm going to have one weight, right? So I'm going to show it in this form. You see? I'm going to show it weights of node J in layer L. And for I, I'm going to put double dot, right? So I'm going to say anybody, right? What is the size of this vector? What is it? How many weights do I have here? WL minus 1 plus 1 again, right? For every, it's exactly the same size as the output vector, right? Because for every single output, I have one corresponding weight, right? So I have one vector coming totally from my previous layer, right? And that vector has a corresponding weight vector, right? Everybody in the weight vector is going to get multiplied to this guy, to the corresponding entry, and then I sum them up, right? Everybody's cool? Clear? So how can I write down that operation? If I have two vectors, I multiply their corresponding entries, and I sum them up. What is that? There's a dot product, inner product, right? So I can actually write down all of that summation as inner product of this vector with this vector, right? This is what we are going to do. So I am going to say that, OK, this is the output, the soft outputs, the soft computation of my node J, my neuron J, in layer L. And I can simply, I mean, this is this form, right? This summation. And I can simply write down this guy to be this vector of weights inner producted with the vector of the outputs in the previous layer, right? So this guy contains everybody here. So this one is getting multiplied with the corresponding, plus second one multiplied with the corresponding, and so on, right? So the same summation is going to be written in this form, yes? So when we measure the width of a layer of a hidden layer, do we count the dummy as well? Like, if you want to just implement it from scratch, it totally depends on you. If you're talking about PyTorch, usually you don't do it. So PyTorch automatically do that for you. Yeah. So you just say bias is true, then it's automatically add those dummy ones. So you don't really need to do that. So we just specify the number of neurons. Yes. So you're going to tell what is this WL minus 1, and then what you want to have as WL. And then when it wants to just build the weights, it's going to add this dummy one here as well by its own. And this is good.
So it's like the summation you did in the previous slide.
Yes. Yeah. Yes. Yes. Questions? No question? OK. So the soft information calculation is essentially one inner product, right? That's it. And this weight vector is specific to the neuron, right? If I change the neuron, this weight vector is going to change, right? So this is important to pay attention here. Everybody's looking here? So you look at this one. We are computing the output, the soft output of node J, neuron J in one layer, right? Now, if I change the neuron from one to another in the same layer, right, J is going to change, right? But when I want to compute the soft computation of the other node, what does change in this computation? What does change? Only weights, right? Does the input from the previous layer change? No, right? You see that this y has no index j in it, right? The previous layer is getting connected to anybody, right? So the input coming from the previous layer is the same, right? The only thing that is changing the computation in one node to another is the weights, right? So this neuron has different weights, is going to compute different things, right? So it means that the first layer gave me a bunch of numbers, a bunch of features about my input, right? Now every node in this layer is using different weights to process those features differently, right? And it's going to extract its own specific features, right? Everybody's cool? OK, so that's about this. And now I can again construct the whole bunch of computations that I have done in this layer, right? So I have WL different neurons in this particular layer. Every single guy in this layer is doing his own computation, right? So I can, once I have done the computation, I can put them again inside a vector, right? And that vector is going to look like this one, right? OK, so now if I want to just see what's going to happen next for the output of this layer, I am going to just activate my computations, right? So this means that I get this activation function. It could be a ReLU, it could be sigmoid, it could be anything, right? I put that function, and then every single entry is going to pass exactly through this guy, gets activated, right? Everybody's cool? So this vector YL, what is its dimension? Is exactly WL, right? So first guy, this ZL1 is going to pass this activation. It gives the first entry here. Second one pass this activation, gets the second entry here, and so on, right? Everybody's cool? Now, one tiny thing that I need to fix here is that, look at this one here. Look at this YL minus 1. When I wanted to do this computation here from the previous layer, what was the size of this vector? It was the width plus 1. And what is this first guy here? This is the dummy input, 1, right? So if I want to go from this layer L now to the next layer, I need to put the dummy 1 there, right? So this is what you usually do in practice, right? Like if you want to write it down algorithmically, after doing this computation, so activating everything, you add 1 here, right? So to just add that dummy 1. Know that you add this 1, then the process of going from this layer to the next layer is exactly as before, right? Every guy in the next layer is going to have its own specific weight, right? Vector of weights, right? It's going to look at this YL, does the inner product, does the activation, gives you a new feature, right? So again, everybody in layer L computed its own features. You have a vector of features. These features are, again, getting processed with every single neuron in the next layer independently, giving you a bunch of new features, right? Everybody's cool? Questions? OK, if you got no question, then this is the whole process of forward propagation. This is the way that the information is passing from the very input towards the very output. So when you start from the first layer, your very first input is your very first Y is your input, right? Your information. You're going to get this input, right? You multiply them with the weights, right? And then you're going to do the calculation. You're going to do the soft computation, right? Once you have this soft computation, the next thing that you're going to do, you're going to just activate it to get your activated features, right? And the only tiny thing that you should pay attention is that every time that you want to do start the process, you don't forget to add the dummy 1, right? Which is going to take the care of bias, right? So I have my input, I put the bias, everybody does its own calculation, activates, I have a bunch of new features, right? Again, you add 1, everybody next is going to do its calculation, activation, and so on, right? And this is the way that the process is going on, right? Everybody's clear? Now, the first layer is eventually doing some raw feature calculations, right? It's going to just look at the immediate input and try to just extract what is inside that, right? But the next layer is getting a sort of filtered features, right? Maybe better features, right? And you're going to do much better calculation, maybe, right? And they're going to keep on going towards very end. At the very end, you have very good features, right? Maybe you wanted to classify this image. Now, the first layer said, well, there are some white dots here, black dots here. The second one says that the black dots is making a curve, and then it gives a bit of clue, right? When it makes a curve, it cannot be, for example, 1 or 7, right? And then the next one is telling you there are actually 2 half circles in it. Well, it could be 3, it could be maybe 8, right? And then the next one just concludes more features. There is no complete circle. Well, this cannot be 8, so I conclude this number was 3, right? So as the input, you put the handwritten number, and then you start to extract features till the output gets clear about the features, right? All the features are there. Half circles are there, no full circle. 2 of them are there. It's only 3 that could happen, right? So this is the number 3, yes? Well, this intuitively speaking, I mean, there are approaches like, for example, XAI, explainable AI, right? Where you try hard to just go on those, hidden layers and find out whether you can infer what is really captured as featured there, right? But you cannot say it like for sure for more complicated models, right? So this is just intuitive. But what we do know is that there are features that are correlated to the input, and potentially they are better distinguished in terms of like type that could help you in conclusion. It's like you close your eyes and somebody's trying to help you what is written on the page, right? And then you start to ask features, right? So is it a number? Yes. Does it have edges? No. Does it have half circle or full circle? Just half circles. How many of that? 2. Okay, that's 3. Right? You're going to say it like this. Yeah. Questions? Everybody's clear? Okay. So this is the forward pass algorithm, forward propagation. So you're going to keep doing this, and at the very end, you're going to give as the output the activated and soft information that you calculated in every single layer. Okay? So you're going to do that. And this is very important. This is extremely important that you give both Y and Z, both of them. Because when we want to backpropagate, we need both of them to be able to compute the gradient. Okay? So you're going layer by layer, but your algorithm, as the output, what it gives you like, this is the first hidden layer, what was computed before activation, what was computed after activation. This is your second layer, what was computed before activation, what was computed after activation, right? For your purpose, for inference that you're doing, you only need the activated last output. That's for sure, right? But if you want to be able to train this network, you need to know all of those single entries to be able to move backward. Why backward? Because you want to compute the gradient of your risk function with respect to every single weight you have inside this neural network. Everybody's clear? Okay, so if you got no question, let me just give you a very quick wrap up here, and then we're going to start from here next time. So looking at these guys, as I told you, every single one can be written in form of an inner product. And as we talked about this, in this inner product, the only thing that is changing by the index of the neuron is essentially this weight vector, right? Y is the same everywhere, right? So I can take Y at the output, right? And what I could say essentially the soft computation vector completely in one layer is one giant matrix multiplied with the output of the previous layer, right? Everybody's cool, right? So what I can do, I can say I have this big matrix WL, which is containing all the weights connected from the previous layer to the next layer, right? And then that matrix, if you consider this one, and you multiply it with the output of the previous layer, this is going to give you the soft computation of the next layer. Essentially, you are just getting a matrix of weights, multiplying it with your previous layer output, right? And then from one layer, you go to the next one, and so on, right? And the dimension of this guy is quite easy for you, right? So number of lines that you have, number of rows that you have is exactly the number of neurons you have in your layer. Number of columns is the number of neurons in the previous one plus 1, and this one is the dummy one that we have, right? Huh? Okay, and you can then simplify this forward propagation algorithm in this form. Instead of writing those particular computation for every single node, you can just compute the whole vector of calculations in one shot, right? So you have the matrix of the layer, you get the output of the previous layer, you multiply, you get the whole Z. You add that one to just keep everything consistent, And then you activate, right? And you keep on going forever, right? And then at the very end, again, you're going to give every single y and z, right? So this is what we call a forward pass, forward propagation. And this is the way that the neural network starts to get sensing about what comes into it, right? Now, the key question remains is that if we want to train this guy, we need to know the gradient with respect to every single weight in this architecture, right? And this sounds like a nightmare, but when you use chain rule, it's not a nightmare, right? It's a less nightmare, okay? So next thing we're going to do, we're going to talk about back propagation, which is the key algorithm helping us doing the training, okay? See you on Friday.